Hello and welcome back to another LeetCode problem. So today we're doing binary tree maximum path sum, and the question is, a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum is the sum of path nodes in the path. Given the root of a binary tree, return the maximum path sum of a non-empty path. So for this root 1, 2, 3, the path is 6. Which means our path is going to look like this. It's going to be this path right here. And then for this, it says it's 15, 27. So it's this path right here. So the path can be any path that is non-empty. So it's something like this can be a path, or it doesn't have to go all the way down to a leaf node, or even just a root itself can be a path, I believe. Like this could be a path, I think. Let's see. Path is a sequence of nodes where each pair of adjacent nodes is a sequence. Path sum is a sum of a node's values in the path. Yeah, so actually maybe, I think actually the path has to be, yeah, I'm pretty sure this is a path, but it might be this, but we'll double check. We'll look at the requirements. So anyway, either way, so how do we do this problem when we do this maximum path sum? So the problem is that the path can include a root and a left and a right, so it can be something like this, or even like this. But how do we get those values? Like, how do we traverse this tree, and how do we get this maximum path? So for one thing, we can note that the nodes values can be negative, so that's important because we don't want to just keep adding nodes in a path, because let's say this is 20 and this is like -7, we would actually not even want to include, like if this was the longest path, we would not even want to include the node. So we don't want to just take the longest path, because sometimes you're going to want to cut nodes out of a path. And so let's figure out how we can get the path at a node, how we can get the maximum path, let's say, at a node, and then what would we return for the recursive case. So first of all, when we are at a leaf node, it's pretty simple, right? The path is just going to be, yeah, I will double check this, but I think a path can be one node, so the path is just going to be the node's value, right? Because it doesn't have a leaf, it doesn't have a left and a right. So that's pretty straightforward. But how do we get the maximum path starting? And so our maximum path is going to have to cross some node. So it'll make this V shape crossing some node, or it will at the very least take a left and a root, or a right and a root, or just the root itself. So what we can do, this is actually, problem is not that hard once you realize kind of what you're looking for. So we have this left path, and we have this right path. And what we can simply do is, if the left path or the right path is negative, we can say that that part is 0 because we're not going to be including it. And so our path can simply be path equals left plus the value of the root plus the value of the right. But these left and right can just be whichever one is greater, either the value or 0, we can pass that in. So if these values are negative, we can just make that 0. So we can do something like max, for example, for the right, we can do something like max 0 right or something. And then we can do the same thing for the left. We can do max 0 left, and that will ensure that if we have negative numbers, we won't include them in the path. So that's how we get the path at a node. But how do we return up, right? So how do we, like, let's say we try to get the path here, but then what are we returning up here? What is our recurrence relation? Well, we need to return up the longest possible part of a path that this can actually use. And so if our path starts at some previous node, then that path can use this node, but then it can only use either the left or the right. So it can only make this V shape once. So if the path is here, it can only go like this. And then it can use this node, but then it has to either go here or here. It can't go to both. It can only diverge once. And so when we return, we need to return the root value, and then the greater value of the left or the right value, or 0, right? So we need to, because if these are both negative, we would just want to return this value. And so let's take a look at what that would look like for this example, for this bottom example. So let's say we are going to recurse all the way down. So we go down to this 9. We say, okay, left is 0, right is 0. So our path, and let's just have a path, and we're going to start it at, let's say we're going to make it equal to the value of the root. That's just a simple, so path is -10, and then we're going to be checking. So we're at 9, left is 0, right is 0. So the maximum path from this 9 is 9. Is path greater than our current path? Yes. So we're going to change this to a 9. Now we're going to return, remember we're going to return the node. We're going to return this node and the greater of the left or the right. So in case these are both 0, so we're just going to return 9. So we're going to return 9 up here. Now when we're at this node, the path at this node is going to be 9 plus, let me actually get 9 plus this, plus something over here. So we're going to recurse down here. Then we're going to recurse left, let's say. Then we're going to be at this node, and then we're going to say our left and right is 0. So our path from here is 15. Is our path greater than 9? Yes. So 15. And then we're going to turn, once again, we're going to turn 15, and then the greater of the left and the right, which is going to be none. So we're just going to turn 15 up here. Now, once again, this node, the path from here is this node plus one of these. So now we're going to recurse down to this right node. Okay, the path here is -7. And so yeah, it has to be a non-empty path. So the path here is -7. Is our path greater than this 15? No. Okay, so now we return -7. So there's a -7 here, there's a 15, and there's a 20. So what's the greatest path from this 20? Well, remember, we're going to take the max value of either the value that we're returning or 0 on each side. So on the right, we're going to have max of -7 and 0, which is going to be 0. Then on the left, it's going to be max of 15 and 0, which is 15. So this greatest path is going to be 20 plus 15, which is this path right here. So that's 35. Then we are going to say, is that path greater than our path? Every time we look for a path, we're going to say, is that greater than our current path? Yes, it is. And this current path is going to be defined outside of the recurrence function. So now we need to figure out what is this returning. So actually, sorry about that. Okay, so we need to figure out what is this returning. Well, we can only return one side. We don't want to return the right. We want to return the left. So we're going to return 35. So it's the node plus the left. So we're going to turn 35 up here. Then here we are going to say, okay, this path is going to be this value plus the left and the right if they're non-negative. So it's going to be 35 plus 9 minus 10, which is 34, right? I think I might have missed one of these paths, so let me just double check. Yeah, okay. Yeah, so I think I did. So the optimal path is 15, 27. So that's interesting that, did I make this negative accidentally? Or is this just wrong? So hold on, let me go back here. Optimal path is, yeah, 15. So I believe, unless I copied this incorrectly, this 1527 should not be right, I think, because this is a -7. But we're gonna look at the problem because I think this is not the optimal path. This would be 35 minus 7, which would be wrong. The optimal path would actually be just 35, I believe, because the optimal path here is -1 plus 20, and then this would be plus 15, so that's 34. Yeah, so I think, so let's look at the problem real quick, and let's just, oh, okay, so this is positive. So that's what I did wrong. So if this is positive, then yeah, then our optimal path would be this path right here, which would make sense. So it'd be 35 plus 7, 42, and it's the same concept. So the path here would be 42, greater than this. Then we were to return the value of the node, and then the biggest of the left or the right. So the biggest is going to be 15. It's bigger than 7. So we're going to return 35 up here. And then when we return 35 up here, it's going to be 35 minus 10 plus 9. So that's obviously lower than this. So our final output is going to be 42. So basically our algorithm, at each node, we're going to figure out what's the biggest path using the node. And then we're going to return the node plus either the left or the right if one of them is positive, or just the node itself if the left and the right are negative, because we wouldn't want to include that in the path. So if this is like -7, and this is -15, and this is 20, then we would just return 20 because these make the path worse up here. So that's going to be our recurrence relation. We're going to check, is the path bigger? What's the path at the node? Is it bigger than our previously calculated path. If it is, we replace it, and then we just return the biggest side, left or the right, or 0. So let's code that up. And let's take a look. So the number of nodes in the tree is 1, 3 times 10 to the 4th. Okay. Binary, node can appear. Note that the path does not need to pass the root. Path sum is the path sum of the node's value in the path. Yeah, so it's a non-empty path. So I do think that a path can be one node. I'm pretty sure about that. But we would let's just code that up and let's see if that works. So I think a path can be one node. I'm pretty sure. Okay, so let's see. So we need to have a helper function, right? And we need to also have this path variable. So we can just have a path variable that we define in here. Yeah, so self.path equals 0, let's say. This would actually not be path. I think we can just do this, and then we can change it in here. So path equals 0. The other thing we can do is, let's just actually declare it in here. Path equals root. So our root has to be non-empty because we have one value. Or do we have? Let's see. Yeah, so we have one node, which means I think our root has to be non-empty. Pretty sure. Okay, but yeah, so let's just do that. So this is root.val. So now we have a helper function. So def, let's call that traverse. And then we're going to have a node. And that's all we need there. So remember, what we're going to do is we're going to get a left and we're going to get a right. So left equals traverse, or sorry, there's one more thing. So if not node, we're just going to return 0 in that case. Because if we get to like the right child of 3 and it's 0, that means the path is just 0. So if not node returns 0, now we do the left and the right here. So left equals traverse node.left. And so we're going to add a little something here. Right equals traverse node.right. So we're actually, instead of just doing this traverse, we're going to have a max, remember, because if it's negative, we want to take the maximum of it with 0. So it's max 0. Then the traversal, same thing here. 0 with the traversal. Okay? So now if it's a non-negative value, we're going to include it. Otherwise, we're going to 0 it out. So then we're going to have a non-local path here that we're going to add from here. And then what we need to do is we need to check, is the path bigger than our current? So our current biggest path is just going to be left plus node plus right, and these lefts and rights will be zeroed out if the nodes are negative. So path equals max path left plus node.val plus right. The path at the node always has to include the node. Okay, and now remember we can return the max of left plus node.val or right plus node.val. So let's see if our path being one node or whatever is a mistake. But so yeah, we're just going to take left plus node.val or right plus node.val. And if these are both negative, then these are just going to be 0. So it'll just be node.val. So I believe that's it there. And I think that is all the code we need. I'm pretty sure, but let's just see. So then we need to call this traverse function root. Let's see if we can have like a null root or something like that. And hopefully that made sense. Okay, none. All right, so we need to return path. Okay. Okay. Okay, so it looks like we can have a non-zero, so our path can be one node in this question. It is a little weirdly worded where it says the path is the sum of the node's values in the path, and it's a sequence of adjacent nodes, even though technically we just have the one node. We can have a one node. So hopefully that makes sense. It's a pretty straightforward problem once you understand the recurrence relation and how you get the path at every node. So let's figure out the time and space complexity here. So time, space. Okay, so for time, we're going to be going down to every single node one time. It's going to be recursive through every single node. And so yeah, so we have to go to every single node, which means it's going to be the n. So it's going to be big O of n, where n is the number of nodes. Okay, and yeah, that's it. It's just going to be big O of n, where we just do a depth first search down the tree. Okay. Space. Are we making anything extra? So we do have to be careful space for a recursive function, you do have to figure out what's the maximum recursive call stack you can reach. So the maximum recursive call stack, so let's take a look. Path in a binary tree. Okay. Right, so this binary tree isn't guaranteed to be balanced. And so we can have something like this, right? And then this would recurse all the way down here. And so the actual recursive call stack would be n here. And same thing, n is number of nodes, because if our binary tree is not balanced, then our space is going to be big O of n. But on average, if the binary tree is close to balance, it's going to be log of n. Right? So in a balanced binary tree, we're only going to be going down. We're going to be cutting the tree into half every time. So this is going to be log of n in the average case and n in the worst case. Okay, so that's all for this problem. And if you like this content, please like and subscribe, and I'm going to make more videos in the future. So, and if you have any comments, let me know in the chat. Thanks.